Press one handle and the evidence leaves the room in seconds. Clean water arrives, waste disappears, and a small pool seals the pipe behind it. The toilet looks like the whole machine because the rest of the machine is buried. Under the floor, one pipe joins another, then another, until the household becomes part of a citywide flow. The waste has not vanished. It has started a journey that needs gravity, pumps, treatment works, trained workers, and somewhere safe for the water to go. Before those systems, the journey often ended in a pot, a backyard pit, an alley, or the nearest watercourse. The smell stayed close enough to identify. So did the flies, the cleanup, and the risk of contamination. A modern flush hides distance better than almost any household object. It lets one room appear clean, while thousands of people and machines handle what left it. This episode follows sanitation in Britain and the United States, from household privies to municipal treatment, without treating that path as universal. At night, many people used a chamber pot because the privy stood outside. In the morning, somebody still had to carry and empty it. A privy might place a wooden seat above a pit or a lined vault. National Park Service archaeology shows that urban wells and privies could descend 15 or 20 feet into the same crowded lot. One structure supplied water while the other received waste. Distance, soil, brickwork, and groundwater determined how separate those two systems really were. A cesspit did not remove anything from the property. It stored liquid and solid waste until the pit leaked, overflowed, or was emptied. Rain could raise the water level and move contamination through the surrounding ground. Full pits attracted insects and produced gases that entered yards and buildings. Not every household threw waste into the street, and many communities developed rules for managing pits and privies. Those rules worked only when owners followed them and someone performed the removal. A backyard solution became less forgiving each time another family moved into the block. Privies and cesspits created a job that was usually done after dark. Night soil workers entered rear alleys when most residents wanted the work kept out of sight. They opened pits that might have been filling for months. Waste was shoveled, ladled, or pumped into containers and loaded onto carts. The work combined confined spaces, heavy lifting, unstable footing, and direct contact with human waste. A narrow passage could force workers to carry each load through the house or beside sleeping rooms. Historic England records alleys designed behind rows of houses so night soil workers could reach the pits. The collected material was often sold to farmers as fertilizer. Urban waste therefore moved through a market as well as a sanitation system. When demand was strong, the contents of a pit had value. When removal cost more than the material could earn, owners had an incentive to delay. Before buried sewers, a city's cleanliness depended on workers whose labor most residents preferred not to see. A pit that served one household behaved differently when it served a crowded tenement. More residents produced waste faster than the ground or collection schedule could absorb it. At 97 Orchard Street in New York, 4 wooden privies and 1 water source served the building's residents for more than 40 years. The rear yard was also used for cooking, cleaning, laundry, bathing, and children's movement. Water collection and waste disposal occupied the same small shared space. A careful tenant could scrub a floor, but could not enlarge the yard or rebuild the sewer. Wealthy New Yorkers began installing indoor flush toilets in the 1860s. Many working-class tenement residents still relied on chamber pots and outdoor toilets into the 20th century. Sanitation reached households according to rent, ownership, law, and neighborhood investment. Women and domestic workers often carried water upstairs and carried waste back down. Children crossed dark stairs and exposed yards to reach shared facilities. Landlords could postpone improvements when laws were weak or poorly enforced. Personal cleanliness could not compensate for missing pipes, overcrowded privies, and contaminated water. A flushing water closet looked like a complete answer because it cleaned the bowl. Alexander Cumming patented an early water closet in 18th-century London. Its curved trap retained water and helped block sewer gases from entering the room. Later siphon designs used a strong rush of water to pull waste through the bowl and trap. The Smithsonian records late 19th-century American models using 5 to 7 gallons for one flush. That performance required an abundant water supply. It also required sound joints, a sloping drain, ventilation, and somewhere for the discharge to end. Without those connections, a water closet merely filled a cesspit faster or sent waste into an old drain. Flush toilets sharply increased the volume of wastewater a city had to carry. Old channels built for rain were asked to receive household sewage. Some emptied directly into nearby rivers. Historic England notes that early flush toilets displaced London's problem from the home into old sewers and the Thames. The new fixture solved an immediate problem for the user and handed a larger one to the city. Cities often expanded the water supply before they could manage the wastewater it created. Early New Yorkers drew from local wells, springs, and the polluted collect pond. Contaminated water contributed to the city's 1832 cholera epidemic, which killed about 3,500 people. Croton water reached New York City through a 41-mile aqueduct in 1842. The arrival was celebrated with fountains and a parade. Abundant piped water supported faucets, bathing, industry, and eventually more flush toilets. Every gallon delivered to a building could become a gallon that needed drainage. A water system without sewers could overwhelm yards, cellars, and old street drains. A sewer system without protected drinking water could send contamination toward another intake. A well beside a privy kept supply and disposal dangerously close. A distant reservoir separated drinking water from the crowded lot. A well-planned sewer separated waste from the household water source. But a city could clean its homes by making the river dirtier downstream. Sewage threatened health through more than its odor. Cholera spreads when people consume water or food contaminated by feces carrying the bacterium. Most early 19th century doctors did not know that mechanism. Many blamed miasma, the foul air thought to rise from rotting material. The theory seemed plausible because the worst smells often surrounded the worst living conditions. Removing filth sometimes improved health even when reformers misunderstood why. But smell could not explain why apparently clear water made a household sick. It could not identify contamination that had no strong odor. A campaign aimed only at bad air might clean a street while leaving a polluted pump in use. Sanitary reports also mixed observation with moral judgment. Poor and immigrant residents were sometimes blamed for conditions created by low wages, weak laws, and neglected infrastructure. Disease was treated as evidence of bad habits instead of unequal exposure. Repeated cholera epidemics made those explanations harder to defend. The argument began to change when investigators followed where sick people obtained their water. London physician John Snow argued that cholera traveled through contaminated water. During the 1854 outbreak around Broad Street, he examined death records and spoke with local households. He mapped where the deaths occurred. Many clustered around a public pump on Broad Street. Snow asked what the victims had drunk rather than what the street smelled like. He also investigated exceptions, including people who lived farther away but preferred water from that pump. Local officials removed the pump handle on September 8, 1854. The famous gesture did not end cholera everywhere, and the outbreak had already begun to decline. Its importance came from the evidence used to justify the action. Snow also compared districts served by two water companies. One company had moved its intake upstream, away from London's sewage. The other continued drawing from a more polluted stretch of the Thames. The source of household water predicted the risk more clearly than neighborhood air. Snow supplied a method for connecting individual deaths to shared infrastructure. Debate continued until Vibrio cholerae was isolated in 1883. By the 1850s, the Thames had become London's largest open sewer. Local drains released sewage into a tidal river that also supplied parts of the city's water. In the hot summer of 1858, the smell became known as the Great Stink. The Houses of Parliament stood beside the river and could not escape it. Members feared the odor itself would make them ill. For once, the people controlling public money experienced the sanitation crisis at their own windows. The Great Stink did not invent the idea of a new sewer network. Engineers and reformers had already produced plans, reports, and years of argument. The heat and smell changed the speed of the political decision. Parliament authorized the Metropolitan Board of Works to proceed. Its chief engineer, Joseph Bazalgette, designed a system to intercept sewage before it entered the central Thames. The project was approved partly for the wrong medical reason. It still protected people because the engineering separated sewage from much of the water they consumed. Bazalgette's system joined local street sewers to large intercepting sewers running east. The completed network included about 1,300 miles of sewers and 82 miles of main interceptors. Many tunnels used an egg-shaped section that kept shallow flows moving along a narrow bottom. Gravity carried most of the sewage along carefully calculated gradients. Pumping stations lifted flows where the land would not cooperate. Abbey Mills and Crossness turned sewage pumping into monumental public architecture. New embankments beside the Thames concealed sewers, roads, and other utilities inside reclaimed land. For roughly 9 years, workers excavated streets, laid brick, handled cement, and built beneath a crowded city. The project consumed hundreds of millions of bricks. Its generous capacity allowed the network to serve a population larger than its designers first faced. The main system opened in 1865. Cholera returned to London in 1866. The deaths were concentrated in eastern districts, not yet fully connected to the new sewers. The pipes worked only where the network reached homes and protected their water. A missing connection could become the boundary between ordinary life and an outbreak. The new sewers did not destroy the waste. They carried it east and discharged it into the tidal Thames below central London. Communities near the outfalls inherited what the city had moved away. In 1878, the pleasure steamer Princess Alice sank near a major sewage discharge, killing about 650 people. The disaster forced more attention onto the condition of the downstream river. From 1887, large tanks stored and chemically treated sewage so solids could settle. The remaining liquid still entered the river. Sludge was loaded onto vessels and dumped at sea. Distance had increased, but disposal remained the guiding idea. Sewers produced an enormous public health gain while leaving an environmental problem unfinished. Collection and treatment were separate achievements. The buried pipe was only the first half of a modern sanitation system. Wastewater treatment plants expanded rapidly in the United States during the 1920s. At the entrance, screens removed rags, sticks, and other objects that could damage equipment. Grit chambers slowed the flow enough for sand, cinders, and small stones to settle. Primary tanks allowed heavier organic solids to sink while grease and floating material rose. Secondary treatment used microorganisms and oxygen to consume dissolved organic matter. The sludge that remained still required handling, digestion, reuse, or disposal. A modern plant therefore depends on operators, laboratories, pumps, maintenance crews, and constant monitoring. Some older cities carry stormwater and sewage in the same pipes. Heavy rain can overwhelm those combined systems and release untreated flow. The flush works safely only when every stage beyond the bathroom keeps working. New York's 1867 tenement law required privies, drainage, and sewer connections on paper, but enforcement remained weak. The 1901 Tenement House Act forced older buildings toward running water and interior sanitation. At 97 Orchard Street, indoor toilets arrived only in the early 20th century. A law mattered when inspectors, owners, plumbers, and public works turned it into a working connection. Rural homes and places beyond municipal pipes followed different paths, including improved privies and septic systems. The absence of smell in a modern bathroom can make the sanitation system seem effortless. In reality, the flush is the first handoff in a long, controlled process. A broken pump, blocked sewer, failed treatment stage, or flooded outfall makes the hidden network visible again. Modern sanitation did not arrive because earlier people suddenly learned to be clean. It arrived when cities accepted waste removal and treatment as shared infrastructure, funded it, enforced connections, and relied on workers who still perform the dirty part of every flush.